Hello, today we're going to talk about reactivity 3.4.11 and 3.4.12. These are HL only topics, and we are going to look at the mechanism of electrophilic addition reactions. So let's quickly review what electrophilic addition reactions are. We talked about this in a prior section, but effectively you're going to have a double bond or a triple bond between two carbons. And remember that when you have these multiple bonds, the first one is sigma bond, and the second or third, if there is one, will be a pi bond. And when you react that unsaturated compound with an electrophile, the pi bond breaks. So the pi bond is broken, and you're left with a new alkane, and your electrophile gets added across the double bond or across the triple bond. So that's the kind of basics of electrophilic addition. Okay, so let's go over the mechanism for this. There's two steps. First step, you're going to have your compound with the pi bond, and it'll be reacting with something, and there's different options that it could be reacting with, but let's start out with just a halogen. So we'll talk about halogenation first. So let's say I have our bromine, Br2, like this. Okay. So what's going to happen, and you remember you always draw curly arrows from where the electrons start to where they're going. So since there's extra electron density in that pi bond, it's going to go this way over to the bromine, and that bond between the two bromines is going to split and will transfer the electrons over to the other bromine atom. Now this is a relatively slow process, so this first step is our slow step, or the rate determining step, and you're breaking that pi bond, so the bromine is going to add on, and the other carbon will have a lack of electrons now. So we formed a carbocation intermediate. You also have this bromine, or bromide really, because it got both of the electrons when the Br broke. Okay, so that's your first step. Your second step, and I'm going to kind of draw it like this just because I'm running out of space in the slide. But now this Br, since it has extra electron density, it can attach to the positively charged carbon here. So the electrons are going to come over to form a new bond there. And we're left with our new alkane with one bromine on each of the carbons. Now this second step is fast in comparison, like that. So that first step is definitely the rate determining step. This is step 2 is our fast step. And you can see that one bromine adds to either side. So anytime you have any of the diatomic halogens, it's going to add one on either side of the double bond or the triple bond for halogenation. Okay, so now let's say instead of adding a halogen across, we want to add water. So we'll start out with our compound with the double bond. And we need this to be happening in an acidic environment. So that way we have our hydronium ions around. And the hydronium ions look like this, with a positive charge. Okay, so the double bond is still going to transfer electrons in here, and then that is going to transfer to the oxygen to break the bond in hydronium and break the pi bond in our alkene. And this is the first step, so it's still the slow step. This is the same basic mechanism. I just wanted to show you what it looked like with hydration. And so you wind up with the carbon now has a hydrogen attached. You have your carbocation intermediate here. Still our slow step. and you have water. Then the double bond, the lone pair of electrons, the lone pair of electrons from the water can be transferred over to the positive charged carbon from the carbocation in our second step, in our fast step, to add like that. But then one of the hydrogens actually leaves to regenerate our hydrogen ions. And if we wanted to show the complete picture here, well, let me draw it. So we had our hydrogen. The OH attaches like this. And then you're left with a hydrogen ion. Well, if this is happening in acidic solution, you have additional water molecules hanging out. And so because of that, it's going to form another coordinate bond there to make this regenerate the hydronium ion that's present. So yeah, so this is very similar. I just wanted to show you how it's using that acid medium to get the water to add across the double bond. The pi electrons attach to one of the hydrogens in hydronium, which makes a water molecule and a carbocation intermediate. And that's our first step. The second step of the reaction, the water molecule will lose one of its hydrogens and attach the OH to that carbocation, and the hydrogen ion will attach to extra water molecules in the solution to reform that acid. Okay, so now let's say instead of adding a halogen or water across our double bond, we want to add a hydrogen halide. So that's something like HBr or HCl, hydrogen and halide. Because it's not symmetrical, it's going to follow something called Markovnikov's rule. And I'll show you what that looks like. So let's say I have our compound with the double bond, and let's just say, to make it easy, I have a propene. Like this. So this rule only really matters when our alkene is not symmetrical. So if you look down the middle here, this one has a extra methyl group. So it's not symmetrical, so it's going to have a couple different options. And let's say, for example, I'm going to add HBr. This HBr. When this reacts, the double bond is going to attract the hydrogens because they're slightly positive, and the bond is going to transfer electrons over to the bromine, and you're going to add hydrogen on there. Now, there are two possibilities. You could either add the hydrogen in the right part, which turns out to be our middle carbon in propene, like this. And of course, you still have your bromide being formed. Or you could add the hydrogen to the carbon on the end, and your carbocation would be then in the middle, in the central carbon, with the formation of the bromide ion. So do you see how this, there's two carbons that make up that double bond. The hydrogen could add to either one. Now, one is more likely than the other. And the reason for that is whatever intermediate, carbocation intermediate, is more stable, is the more likely reaction mechanism. So you're looking for, if you have a secondary carbocation, that is much more stable than a primary carbocation like this one. So secondary is more stable, and tertiary is even more stable than that. So you want your hydrogen to add to the carbon. That makes your carbocation more stable. So this product of our first step is more favorable, and it happens more frequently. Now from there, then the bromine could add and form a new bond there. So you will wind up with the major product having the bromine on the center carbon, which makes it a secondary halogenoalkane. So this is our major product with the bromine in the middle. Okay, so for this example, it says using curly arrows, draw the mechanism of the reaction between but2-ene and bromine and give the name of the product. So but2-ene will look like this, where the double bond is in the center of the molecule, completely symmetrical. It doesn't tell us whether it's a cis or trans isomer. It doesn't matter for this. And you have bromine. Then it says draw the mechanism of the reaction between them. So I want to draw this with showing that bromine-bromine bond because the double bond here is going to transfer. And so in step 1, we have our first bromine being added. And we have our carbocation intermediate. And then we have bromide. And then for our second step, that bromine is going to form a new single bond. So we are left with our new halogenoalkane with 2 halogens. And the name for this one would be 2,3-dibromobutane, because there's 4 carbons. Doesn't matter which carbon you start numbering at, as long as it's at the end of the chain. 1, 2, 3, 4. And so the bromines are on carbons 2 and 3. There are 2 bromines. It has 4 carbons in the chain, and there's only single bonds. Okay, so for this question, draw structures for the 2 possible products of the addition of BrCl to propene, and which structure is the major product, and explain why. So let's draw propene. I'm going to draw it like this. And this one is not a symmetrical molecule. So when this forms a carbocation, we talked about Markovnikov's rule, where the central carbon is most likely to have that positive charge. So whichever halogen adds first is going to add on that end position. And then the other will come in second. Okay. So our 2 possibilities is that the bromine adds first, and then the chlorine comes in second, like this. And our other possibility is that the chlorine adds first, and the bromine comes in second. So let's think about the halogen that we're adding. We're adding BrCl. Like this. Now, which of those elements is more electronegative? Chlorine has the greater electronegativity of the 2. So if we're looking at this molecule, which is polar, the chlorine has a very slight negative charge and the bromine has a slight positive charge. So because of that, the electrons from the pi bond are going to be more likely to transfer to the bromine first to form our chloride ion. So that means in the intermediate here, our bromine is going to add to the end carbon, and then our chloride ion will come in during the second step, like this. So that means you're more likely to form this first product. That's going to be the major product. because the chlorine has to add a second.